to B. Then if J is a finite and the summation, the sigma of M of I where I belongs to J is less than or equal to M of I. It seems trivial, but we prove it here. But note that the index set J is at most countable. So it is finite or cardinality of J. Okay. We number the intervals I from left to right, so I equals to AI to BI, where I is between I and N, and A is less than or equal to A1, less than or equal to less than B2. For example, we have a figure here. Okay, here we have A to B. Okay, this is A1, A2 to IN. Okay, each of two of these intervals are disjoint. Okay, so A1 is greater than or equal to A plus B1 to A2. Okay, A2 minus B to Bn and we put B minus A. So or equal to M of I. Okay. The claim flows immediately from theorem 1.14 if J is a countable set. We have proved this for finite case. But theorem 1.14 here says that a family of non-negative numbers I is summable if and only if the set of its finite partial sums is bounded above. We have here bounded above by B minus A. If so, the supremum of this set is the sum of the family I belongs to R or J. Now we are able to define the measure of an open set. So let G be a non-empty bounded open set. The bounded open set, bounded is important here because if a set is unbounded, then its length or its measure is infinity. Okay, and let I, where I belongs to J, be the family of its component interval. Its component intervals. Okay. The measure M of G of the set G is the sum of measures of its component intervals because I are mutually disjoint. And we use the previous theorem in order to define the measure of an open set. M of G equals to the summation or sigma M of I, where I belongs to J. And we also set M of the empty set, the measure of the empty set equals to 0. Now, if J is an open set, we defined measure of G, okay? And we go straightforward to define the measure of a closed set. And finally, the measure of any set, okay? Step by step, we go forward. So the measure is a function. Measure is a function from, for example, G to R. G is the class of all G subsets of R such that G is open. So the measure is a function, is a real valued function on the family of all bounded open subsets. And G is open and bounded. باوندد رو چی میگید زینب؟ اوپن رو که میگید مفتوحه.
باوندد یعنی مغلقه، فتره مغلقه میگن.
مغلقه که بسته رو میگید مغلقه.
مقیده بعربی.
مقیده
نعم.
اینو میگفتید مفتوحه. فتره
مفتوحه نعم.
اینو میگفتید فتره مغلقه. حالا باوندد میشه چی؟
مقیده، فتره مقیده.
بله. مجموعه مقیده. bounded set. Okay. مجموعه مقیده. Okay. So M is a real valued function on the family of all bounded open subset of R. In the rest of the section, we establish some useful properties of this function. Okay, we will investigate the properties of the measure function. Theorem 2.2 says that if an open set G1 is a subset of a bounded open set G2, okay, G1 is in G2, then and G2 is bounded, and hence G1. Okay, bounded. Hence G1 is bounded too, yes, because G1 is bounded by G2. Then, and both of them are open. M of G1, the measure of G1 is less than or equal to the measure of G2. It means, it says that the measure function on open sets, open bounded sets is increasing. It's increasing, in a word. Measure is a monotone. Okay, it says here, monotone function on the set of bounded open subset of real numbers. and we can say totally monotone.
Doctor,
Yes.
the monotone function is increasing and decreasing. In your this theorem, if in increasing, you say monotone function.
Yes. We call this property monotonicity. Okay, monotonicity says
Yes, sir.
that if G1 is less than it is here in the meaning of being a subset. Okay, G1 is a subset of G2, then G1 is less than G2.
Yes, doctor.
Okay, it's increasing. We say it is monotone.
Okay, doctor. This
Because
I'm
if G1 is a superset of G2, then
decreasing.
G M of G1 is greater than or equal to M of G2, obviously. Okay. For
Okay,
the
doctor.
proof, let I be the family of component intervals. This is our important instrument in many of the theorem, in proving many of the theorem, component intervals. It is a property for open sets. Every open set, I repeat it frequently, every open set is the union of open intervals, open disjoint intervals, called component intervals of the open set. By corollary 1.1, each II is contained in a unique component interval of the set G2. For you remember the corollary, if a non-empty set G1 is a subset of G2, then each component of G1 is a subset of a unique component interval of G2. So each II is contained in a unique component interval of the set G2. Let us partition the set J into a family of subset J lambda where lambda belongs to capital lambda in such a way that indices I and J are in the same set J lambda if and only the intervals I and Ij are subsets of the same component interval I prime lambda of G2. By theorem 1.16 was the associativity property of addition. We have M of G1 equals to the sigma M of I where I belongs to J. And we partitioned this, we partitioned the set, the index set J with this. J equals to the union of J lambda where lambda belongs to lambda and J lambda intersect with J lambda prime is the empty set. Now, the sigma, the summation of M of I, because of the theorem 1.16, is equal to the summation of Mi over the subsets, over the subfamily J lambda. And we can sum it by capital lambda. And by theorem 2.1, theorem 2.1 says that if II there is a family of pairwise disjoint open intervals that are contained in an open interval I, then we have this one, okay? Sigma Mi is less than M of I. Okay. Now we have this. We have this one, M of I, where I belongs to J lambda, is less than or equals to M of I lambda prime. Hence, M of G1 is equal to M of G1 is equals to this double sum by partitions, and this is less than or equal to M of I prime lambda, where lambda belongs to capital lambda. By the previous corollary, we have M of I prime lambda, the sigma of M I prime lambda, where lambda belongs to lambda, is less than or equal to G2, because each I prime lambda is a subset of G2, and they are disjoint. So the summation of M of I prime lambda is less than or equal to the measure of G2. Now, in as much as the family I prime lambda is a subfamily of the family of component intervals of G2. This is by this. Thus, M of G1 is less than or equal to M of G2.
Doctor,
Yes.
this theorem important?
What?
Important, this theorem?
Important, yes, yes.
Okay.
We use it frequently. It is not important by its own, okay? But it's important in the meaning that it is a tool for the other notions will come later, okay?
Okay, Doctor.
The next theorem asserts that measure is a countably additive function. What is a countably additive function? What is a countably additive function? We say unbounded open sets, of course. We say a function f is countably additive unbounded open set or on a family of sets if f of the union of ai or n equals to 1 to infinity, where am intersect with an is the empty, where m is not empty. Then f of this union is the sigma or the summation of f of n from 1 to infinity. If we have this, then we say that f is a countably additive function. Countably additive. If instead of the infinity we have a finite number of and then we say f is additive. Now here countably additiveness is an important property for the rest of this section. Now let a bounded open set G be the union of a finite or countable family of pairwise disjoint open sets Gi. Okay, so G is the union of Gi where I belongs to J, let us write, put a point here to emphasize that GIs are mutually disjoint. Okay, this is a convention between me and you. When we put a point in the union sign, it means that GI intersect with GJ equals to the empty, where I is not J. Okay? Then M of G. M of G is the sum of M of GI, where I belongs to J. This is a useful theorem. For the proof, for a given I in J, let GI be the union of IJs, where J belongs to II, where IJI is the family of component intervals of the set GI. Okay, every open set like GI has its component intervals. So GI equals to the union of open intervals I. We put I above the capital I to emphasize that this is relative to this I. Okay, for example, G1 is the union of IJ, okay, IJ, where J belongs to J1, okay, J1. For example, G1 is A1 union with I2 to the infinity. Maybe it is infinity or finite. So we don't write it. We can partition these intervals for each open set GI. We have this. GI is the union of IJ to the power of I in the parentheses, to emphasize that it's relative to GI. Now, it is the family of component intervals of the set GI. Now, by theorem 1.8, these intervals IJI for J belongs to IJ are precisely the component intervals of the set G. Okay? They are precisely the component intervals of the set J. Let's have a look to theorem 1.8. If an open interval G is the union of an open set G is the union of a family GI of pairwise disjoint open sets, then each component interval of G is a component interval of one of the sets GIs and the component intervals of sorry. بچه نمیذاره زینب. خب کجا بودی؟ صدا رو داری؟ You have voice?
Yes, Doctor.
Yes?
Yes.
Okay. So by theorem 1.8, the intervals I, j to the power of I for I, j belongs to I, j, I, j, and I belongs to j are precisely the component intervals of the set G. By the associativity property of summable families, we have this M of G equals to the sum of M of each of j ij's. Okay, we can write it M of G is the sum of M of gi finally. Okay, M of gi finally. M of component intervals, component interval. Okay, or the sum of lengths of component intervals, and each of them, sorry, sigma M of component intervals of gi, okay, where I belongs to j and the union of gi is g. And we can write it by the associativity property, then it is equal to the sigma I belongs to j of the sigma j belongs to ij, m of these intervals, and by the thing that I said in the previous page, it is equal to the m of sigma m of gi, where I belongs to j. Now, if we drop the assumption that the family in the theory are pairwise disjoint, okay, then we have a weaker property of measure. You have something like this in the lesson of probability. Maybe you remember probability theory. If P, you have P of A union with B is P of A plus P of B minus P of A intersection with B. Do you remember this property or this identity?
No, Doctor.
احتمال.
احتمالية.
Yes. And we are talking about the measure, because the probability is a measure. Probability is a measure in random variables. And we are generalizing this notion here. Okay? If this is empty P of, if A intersect with P is the empty set, then P of A intersect to B is 0, okay? 0 when A intersect B equals to the empty set. But if this is not the empty set, it's a positive number. And we have P of A union with B is less than or equal to P of A plus P of B. Okay, now we can say a similar thing here for measure. If G is the union if an arbitrary union, not assigned a point, okay? An arbitrary union of Gi where I belongs to J, here it is possible to two of Gi's have non-empty intersection, okay? So finally we have this inequality. M of G is less than or equal to the sum of M of Gi where I belongs to J, okay? Recall that the sigma of mj, m of g, gi is infinity if the family is unbounded. If the family m of gi, where I belongs to j, is unbounded. In order to prove this claim, we need two lemmas. Lemma 2.1 says if a closed bounded interval from A to B is contained in a finite union of open intervals, then the length of A to B is less than the sum of lengths of the open intervals. Okay? The closed interval, closed bounded interval A to B is contained in the finite union of open intervals, finite unions of in, and from 1 to ij, for example, or I from 1 to n, then the length of A to B, B minus A, is less than or equal to the sigma. Let, for example, be the open interval, for example, A, I, E, I. They may have a non-empty intersection be together. The sigma of Bi minus Ai, I is from 1 to n. Okay, you can check the proof by your own. Proof by induction on the number n of opening intervals. Okay, proved by induction. The claim is trivial if n equals to 1. Let us assume that it holds for some n, and let ai to bi are open intervals that I is between 1 and n plus 1. The family of n plus 1 open intervals such that their union contains this closed interval. Without loss of generality, we may assume that B is here between a n plus 1 to b n plus 1. And in the end, you can check it. It is very easy. The other lemma 2.2 says that if an open interval I from A to B is the union of a finite or countable family of open sets. Let us see the previous lemma again. If a bounded, here we have, if a bounded closed interval A to B is contained in the finite union of open intervals, then the length of this closed interval is less than or equals to the sum of lengths of the open intervals. Now, we have this for open interval. If I from A to B is the union of finite or countable family of open sets Gi, okay? Not intervals. Open sets Gi, then M of I is less than or equal to sigma M of J. Because for any open set GI, we have its component intervals. It could be written as a union of disjoint open intervals called its component intervals. And we use this and we prove that m of I is less than or equal to sigma m of Gi. The proof is easy, and we use the previous example, the previous lemma, and we construct a closed interval from the open interval. We have this one, A to B is an open interval. So this is A plus epsilon over 2, B minus epsilon over 2. It is a closed interval and it is a subset of the open interval A to B. Now, the open interval is the subset of GI, okay? Subset of GI, finite or countable, okay? GI, finite or countable. Now, this closed interval is a subset of this union. Each of GI is a union of open intervals, and we call it component intervals of GI. The union, the countable union of countables is countable. Okay. Now, this closed interval will be in a countable union of open intervals, and theorem and the previous lemma says that. What we want. And we have another thing that we use it here. It's called the Heine-Borel theorem. Maybe you remember the notion of a cover. Okay. And the closed interval A plus epsilon over 2, B minus epsilon over 2 is a subset of a countable union of I. For example, I belongs to J, and J is countable. Okay. Heine-Borel theorem says that this closed interval could be surrounded by a finite union of these intervals. Let us check theorem 1.2 again. The Heine-Borel theorem says that every cover of a closed interval by open intervals contains a finite subcover. Okay, contains a finite subcover. So this closed interval from A plus half epsilon to B minus half epsilon is covered by a finite subcover of these i's. For example, A plus epsilon over 2 to B minus epsilon over 2 is the subset of some intervals without losing the generality I from 1 to n, for example. Now we have by the previous lemma that B minus A minus epsilon this is the length of this closed interval. Okay, length of closed interval a plus epsilon over 2 to b minus epsilon over 2 is b minus epsilon over 2. For example, assigning L is minus b minus epsilon over 2 minus a minus epsilon over 2 is b minus a minus epsilon. Okay, so b minus a minus epsilon is less than the sum of m of these I k's relative to i's s is from 1 to n. It is clear that the families m of ik to the i's are summable, and therefore this is less than the sums, less than by the associativity property we have this double sums, and we have this less than or equal to these sums because of monotonicity of the measure. And finally, this is the sum of measures of g I where I belongs to a. Now, because this inequality is holds for an arbitrary epsilon, okay, an arbitrary positive small epsilon, we obtain the desired result that the length of this, the length of this open interval is less than or equal to sum of the lengths of the sets, open sets G. This is a figure for the proof of this lemma. We can say we have an example here. If G is 1, 2, and 3, and J1 is 4-point set, and J2 is 5-point set, and J3 is 4-point sets, then there are n equals to 5 selected intervals labeled by the values of the variable s in figure 2.2. It can be easily seen that you can check it in home. Now, the next step is for a bounded open set G, if it is the union of a finite or countable family of open sets, then M of G is less than or equal to M of Gi. G is the union of Gi, I belongs to J. And the subset Gi could have non-empty intersection with any other of these Gj's, for example. Now, yes, question?
With regard to the numbers theorem, we are required to write the text or our text and proof.
Again, please.
With regard to the number of theorems, we are required to write a text or a text and proof.
You have the book. Zainab.
بله استاد.
چی میگن؟ من متوجه صحبتشون نشدم.
أستاذ علي يقول ما انتبهت شنو ما فهمت.
يعني انا
شنو تقول؟
جاي اقول بالنسبه للمبرهنات هاي الارقام اللي موجوده المطلوب من عندنا بالكتابه اكتبها بس نص، لو نص وبرهان.
ها هسه اوكي. ببخشید دکتر محمد میگن چیز این مبرهن نمیدونم که نظریه‌ای که الان داریم میخونیم خودشو برهانشه یا فقط یعنی نظریه کامل باید بخونیم؟
منظورش اینه که فقط اثباتش فقط صورت قضیه ها یا اثباتش هم میخواد؟ آره
بله.
خب نگاه کنید، امتحان که حضوری نیست، مجازیه، یعنی از راه دور شما امتحان میدید.
بله آنلاین.
بعد آره، و شما کتاب رو هم که دارید. بنابراین خب اگه قرار باشه من بگم این قضیه رو اثبات کنید که خب از روش می‌نویسید دیگه، درسته؟ ولی فرض رو اگه بر این بگیریم که کلاس حضوری باشه، اگه فرض رو بر این بگیریم هر کدام از این قضیه ها هم میتونه سوال باشه. مثلا همین قضیه 2-4 ممکنه سوال بدیم بگیم که مثلا فرض کنید یه مجموعه باز و کراندار جی داریم که اجتماع شمارایی از مجموعه های باز جی آی باشه. اون وقت ثابت کنید که مژر یا اندازه، ما بهش میگیم اندازه تو فارسی، اندازه جی کمتر یا مساوی با مجموع اندازه های هر کدوم از اون مجموعه های جی آی هست. ولی شما فرض رو بر این بذارید که لازم هست اثبات اینها رو بدونید. آره اینو بهشون بگید.
بله. یعنی مثلا شما ازمون میخواین یا نمیخواین؟
خب من بخوام که به نفعتونه. شما کتاب
حضوری فعلا که الان حضوری نیستیم، فعلا آنلاینیم.
آره آنلاین هم خواهید بود، تا آخر ترم هم آنلاینید، این ترم همینه
انشالله.
بنابراین شاید من ازتون نخوام که به نفعتونه بخوام، چون جلوتونه از روش می‌نویسید. شاید من نخوام ولی به هر حال با توجه به درس و رشته‌تون
باید
تا اونجایی که ممکنه بلد باشید. آره
استاذ علي يقول احنا بصورة عامة اذا الدوام حضوري احنا نطلب من عنده الاثبات مال النظريات زين، فبما ان انتم حاليا اونلاين وهاي يعني لازم تعرفون هسه حاليا لازم تعرفون الاثبات، يعني مطلوب من عندكم حتى لو ما اني اطلب، يعني بالمناقشة يطلبون من عندكم الاثبات. ويقول بصورة عامة هسه حاليا انا ما احاسب، بس يعني لازم تعرفون، يعني اقروها، ما معنى اقروها ان شاء الله ما مطلوبة من عندنا. يقول ما اقدر اقول لكم ما مطلوبة، بس لازم تقروها.
تمام بارك الله فيك.
مشكورة.
عفوا. ادامه بدید.
زینب یه نکته دیگر هم بگم و اون اینه که توی اثبات این قضیه ها یه تکنیک هایی میبینید. یه تکنیک هایی میبینید که بعدن که میخواید مثلا یه تمرین رو حل کنید که جوابشو ندارید، اگر اینا رو خوب یاد گرفته باشید و بلد باشید، از این تکنیک ها میتونید اونجا استفاده کنید و اون مسئله ها رو حل کنید، تمرین ها رو حل کنید.
بله.
آره اینو بگو بهشون.
يقول بكل إثبات للنظرية أكو يعني حتى لو أعطيكم أمثلة، يقول لازم عندكم يعني فد شلون نظرية بدائية، يعني بحيث يعني شغلة معلومات بدائية بين أنتم تعرفون تبرهنون. إذا عرفتوا هذين الشغلات البدائية بأي مبرهنة تعرفون يعني تسيطرون عليها تبرهنوها، أنتم يعني مسيطرين بدون أي شيء. يعني كل واحد شلون راس مفتاح لازم يعني تسيطرون عليها حتى تقدرون تحلون. بس احنا بالنسبة لنا كل شيء ما نعرف شنو المفتاح مالته حتى يدخل بالنظرية بالإثبات، ما أعرف. انتوا بعد ما أعرف، انتوا عندكم شيء عن الإثبات ما أعرف. أنا بالنسبة لي حاليا كل شيء ما أعرف عن الإثبات، شلون راح يبدون شلون راح بس يقول هو بكل وحدة يعني نقدر نسيطر عليها بالإثبات.
زينب قصد التعريف.
لا هاي تحكي عن نظريات الإثبات. التعريف خو داخل، هي بكل الأحوال هو ما يجيب تعاريف، ما أتوقع يعني.
لا
تعاريف. النظريات والإثبات. يقول النظرية أنا إذا أعطيك مثلا هاي نظريتين 4 أعطيتك إياها كاملة، وأعطيك أثبت بأن الميجر جي أصغر أو يساوي مثلا السميشن. يقول لك أثبت بأن أنت لازم تثبت هذا إذا أونلاين.
اي ست، هو القصد من عده انه اذا على قصد البدايه المفتاح انه هذا هو التعريف، هو النظريه تتبرهن على اساس التعريف.
نعم صحيح
استاذ، على اساس التعريف، على اساس النص مال المبرهنه. يعني اتذكر احنا
نص مال المبرهنة. إيه هو شو يقول لك شلون لازم تعرف مثلا قلق مال يعني شلون مفتاح الإثبات حتى تقدر أنت من يمك أنت ومغمض تسيطر على الإثبات مالته.
بالجامعه
أثاري به شغلات
موجودين عندنا، تمام. كان يطلب من عندنا بس النص مال المبرهنه، يعني النص المبرهنه مال مثلا 2 ثيورم 2 ثيورم 2 1، فيريد من عندي بس النص على مود ادرجه، على مود يفتهم انه انا اصلا مستوعب السالفه.
هاي شو وقت من يعني مثلا تستفاد منه مبرهنة ثانية، مثلا تكتب نصه غير هيك.
اي بالضبط، تكتب النص مال المبرهنه وتبدي تكمل الحل المطلوب.
بعد ما أعرف، هسه أنا حاليا هو يقول هسه حاليا يعني يقول اقروهن الإثبات مال المبرهنة، كل مبرهنة يقول اقروهن، بس
هو
يقول ما أتوقع
بالنسبه
أونلاين
لنا
ما.
المبرهنات هاي المعلومه اللي يعني المعروفه الموجوده قدام عندنا يجيب من عندها، اما بالنسبه للبقيه هاي يعني المتداخلات ما اصور يجيب من عندها.
أتوقع هو لا أتوقع هو يعني يمكن ما يجيب نصا حسب كلامه هسه من كان يحكي.
هي عايزه وتكتب.
يعني يقول إحنا الرياضيات أعطيكم أمثلة، أعطيكم شغلات تستفادون من المبرهنة وتكملون الفعل يعني.
يلا الله كريم، يلا مشكور ست.
الله كريم.
لا تخف ولا تحزن.
لا ان شاء الله دكتور،
إن شاء الله دكتور
راح نمشيها عديل وتمشي ويانا عديل بحيل الله.
إن الله معنا.
ان شاء الله.
ومعكم. Okay.
شكرا دكتور.
عفوا.
شكرا دكتور.
Please read the proof of this theorem by yourself. It is not very difficult. We want to prove that the m of by the use of the previous two lemmas, we want to prove that the measure of g is less than the sum of measures of gi, where g is the union of gi. I belongs to j. Okay, I belongs to j. You should start with component intervals of G. Component intervals of G, call them ik, where k belongs to k, and you make the intersection of each of these gi with ik and call it eik. Okay, trivially eik is this intersection is a subset of gi. Okay, g is e is a subset of g, so the measure of eik is less than or equal to the measure of gi by the monicity of the measure g. Now, because the family mg is summable, the family meik is summable for any k, and by the previous lemma we have this one for each k belongs to k, and for I belongs to j we have this, and so on to the end of the proof. It is straightforward. Okay, now we have the measure of a bounded closed set. So far, we define the measure of a bounded open set. The measure of a bounded open set is the sum of the measure of its component intervals. Okay. Now, where F is a closed set, what can be said about the measure of F? we have had a theorem in chapter 1, theorem 1.10, says that if F is a non-empty bounded closed set, then the points A and B, infimum and supremum of F, belongs to the set F. And the set, the complement of F with respect to the closed interval A to B means the closed interval A to B minus F is open. So A to B minus F is open, okay? So we define the measure of any open set. So the measure of A to B minus F is defined, okay? It is defined in the previous section. Now let us define the measure of F to B, the measure of A to B, the measure of this closed interval or this open interval A to B minus the measure of its complement, okay? The measure of F is the measure of its complement, which is an open set. Okay, so
closed set.
F is a closed set. Okay, so F is a subset of A to B. Okay, A to B is a closed set. Okay, now A to B minus F is open.
It's open.
Yes, it is
Yes.
open and so has a measure. It has a measure. Now, we define the measure of F to be the length of A to B, B minus A, minus the measure of this open interval, this open set, sorry. Okay, the measure of F is B minus A minus the measure of this open set. This is an open set. Open has measure. Okay, this is the definition of the measure of a closed set.
Doctor, what definition a closed set?
Definition of closed set.
Yeah, this definition of open.
Open. Okay, let me explain you. G is open if for each A in G there exists a neighborhood of A, there exists a delta, for example, positive, such that A minus delta to the interval, open interval A minus delta to A plus delta is a subset of G. Okay, in this case, we say that G is open.
Yes.
Okay, and F is closed. F is closed if
G complement.
For yes, it's complement. If
Yes.
it's
Okay. G
complement
is closed.
Is open. Okay.
Okay.
Now, by theorem 1.11, the class of non-empty proper closed subsets of R. Let me add another student here. Ali Abraham. Abraham means Ibrahim. The class of non-empty proper closed subsets of R is disjoint from the class of open subsets. Okay, because every set that is not open, its complement will be open. Definition 2.3 extends 2.3, this definition extends the function M from the class of bounded open sets to the class of bounded non-empty closed sets. We denote this extended function by same symbol M. Okay, we start, have a review. We start by an open interval, and then we went to open sets, and now we are here, closed sets, and finally we will define the measure of any set. Okay, we are here now. By theorem 2.1, the measure of the open sets A to B minus F is less than the length of the interval A to B. Hence, the function M is non-negative on bounded open and closed sets. M is from G or F to non-negative real number. Okay, let's have an example here. Let F equals to the closed interval from A to B. So A to B minus F is empty. Okay, therefore the measure of a closed interval is equal to the measure of an open interval with the same endpoints. Okay, the measure of the open interval A to B is the same as the measure of the closed interval. In particular, the measure of a singleton is 0. M of a singleton is M of this closed interval, okay? And it is A minus A and is equal to 0.
Can repeat, Doctor, for singleton?
Yes, every singleton A can be written as a closed interval. Yes?
Yes.
Now, the measure of A equals to the length of this interval. The length is 0. Okay?
Yes. Yes.
Okay. The following lemma is instrumental. The result of this lemma will be used implicitly in the rest of this section. Let I be an open interval from capital A to capital B containing a closed set F. Then M of F equals to M of I minus M of I minus I except, for example, except, I read it except, okay? I except F. Okay, note that I except F is I intersect with F complement. F is closed, so F complement is closed too. F is closed, so F complement is open, sorry.
Open, yes.
Okay. I is open too, and the intersection of two open sets is an open set, okay? So M of I except F is the measure of an open set. And I is here is an open set. An open interval is an open set, obviously. So M of F, the measure of a closed set, it's a measure of an open set minus a measure of the other open sets I minus F. Okay, the proof is easy and straightforward. As before, let A be the infimum of F and B be the supremum of F. Then A to B and the sets A to B minus F and I minus A to B are open. They are open and disjoint. Okay. This set is a subset of A to B. Okay, and has no intersection with this. Okay, A to B except F intersect with I minus A to B is the empty. It is empty. That's parenthesis better. Okay, because if X is here, then X belongs to the closed interval A to B. And if X is here, then X is not in the closed interval A to B. So their intersection is empty. Okay, now I except F is A to B except F union with I except A to B. And they are disjoint open intervals. So the measure of these, the measure of this open interval is the sum of these, the measures of these two open sets. Okay, the measure of I except F is equal to the measure of A to B except F plus the measure of A except A to B. And by definition, the measure of this set is equal to B minus A minus the measure of F, and the measure of this one is the length of the interval I minus the length of the closed interval B minus A. And you can simplify this identity by this, and finally you have B minus A minus the measure of F. And you can see another example here. Okay. On time. Are you tired?
Yes, doctor.
Okay, I know.
Just give me 10 minutes.
Okay.
خلينا نشوف ايش قد يكمل. اذا بعد ربع ساعة نص ساعة خلينا نكمل المحاضرة في الدورة.
تمام اوكي. تمام اوكي. اي تمام عاد.
دكتور کی تموم میکنیم اگه رست
خسته
نگیریم؟
شدید؟
اگه خسته نشدیم کی تموم میکنیم؟ نیم ساعت دیگه؟
نه. الان که باید
بهتر که بریم و برگردیم یه رو.
نگاه میتونیم بریم نیم ساعت دیگه بیایم. اگر فکر میکنید که کافیه برای امروز میذاریم هفته های بعد.
الدكتور هم يتعب.
يقول إذا تريدون بعد نص ساعة، وإذا أصلا تعبتوا تريدون خليه على الأسبوع الجاي.
خلوه على الأسبوع الجاي.
كيف الدكتور كيف؟
لا يقبل لا
ببخشن دكتور.
لا ما لا دخل بالموضوع.
ما عنده مشكلة؟
هذا حد.
زين. هسه شنو على الأسبوع الجاي تجون ترجعون فد نص ساعة ربع ساعة؟
إيه هاي تمام.
شنو نبقى؟
قولي الأسبوع الجاي وني.
میگه اگه زحمت نیست تا هفته دیگه.
بسیار خوب.
میگن خسته شدیم یه ساعت نیم.
إلى اللقاء، مع السلامة.
مع السلامة دكتور، مع
مع
السلامة.
الى
أستاذ
اللقاء.
زينب،
Have a good night.
اسألي قولي لي شو وقت الامتحانات
میگن
مع نهاية
امتحانات
الكورس؟
میدونین آخر ترم
نه من نمیدونم، حالا